Hello and welcome to the XP Solutions XP Live webinar. My name is Jessica Jeffries and I'm the Products Manager here at XP Solutions. Today's webinar title is Hydrology 101. We're lucky enough to have two presenters today. XP Solutions Senior Water Resources Engineer Gavin Fields, and we're also joined by a guest presenter, Mr. David Lergesner. David has had a career in education, most specifically in geography education, spanning more than 40 years. David has a BA and a B.Ed from the University of Queensland and a Master of Science degree from Griffith University, also in Queensland. After a career in teaching, David has lectured in geography at both Griffith University and Queensland's University of Technology. David has also written 4 books in his own right on people and environment and geomorphology, as well as being a significant contributor to the Cambridge series Geography for the Australian Curriculum. David's passionate interest is sharing how a knowledge of geography is fundamental in seeking solutions to people and environmental management issues locally and around the world. So today we'll run through first a brief introduction, then discuss the physical characteristics of hydrology, look at various different rainfall methods, routing methods, talk about how you present hydrological results, and how hydrology affects 2D methods as well, followed by our question and answer session. For those of you who don't know XP Solutions, we're a software company for modeling wastewater, stormwater, and flooding. We have an advanced graphical user interface and analytical engines. The software produces CAD and GIS type interface and data management tools, as well as graphical reports, maps, and animations. We have hydrological methods built into the software, 1D analytical engines, and 2D analytical engines embedded as XP2D. So why is this important? Well, obviously there's a wide range of people that use hydrological data. In agriculture, it's very important to know what happens when we receive rainfall onto the land and how that runs off and how we manage that water. When we're planning towns and cities, we need to know where the stormwater will go and where the risk of flooding is in order to make sensible decisions about development. And in other areas of engineering, we need to assess the change. And you'll hear more about that from our speakers during today. So first, I'd like to welcome David.
Thanks very much, Jessica. It's great to be here today at part of this presentation. Let's kick off at the start of the thing, and that's the hydrologic cycle. Probably most of us are familiar with this sort of diagram we've got up here now. We get the evaporation off the ocean, we get condensation into clouds, clouds move inland, they're pushed up by the mountains, rain falls, rain and precipitation in various different forms of ice and snow, snow, sleet, rain, and of course this eventually runs off down slopes and either into streams, into storages, and finds its way back to the ocean where the cycle begins again. Right, and most of the things that we're looking at, of course, in terms of managing water and looking at hydrology is looking at catchments on the Earth's surface. There are various sizes of catchments on the Earth's surface, and the important thing is that a catchment is an area which collects all the runoff from a particular area, directs it to a low point such as a stream, river, or lake sometimes, and sometimes it'll go to the ocean, but if it's an internal place like Australia, a lot of it might evaporate internally. Right, the boundary of a catchment is known as an interfluve, French word meaning between rivers, and in this slide here we've got the actual boundary of the catchment. The interfluve is actually followed by the road, and roads often do follow those sort of areas. You can see on the left hand side the water's running into one catchment area, on the right hand side the water's running into an entirely different catchment area. As I said, catchments vary in size. This is one of the smallest I've seen. Fascinating little one here in Kelvin Grove in Brisbane, and I was just lucky I got that photograph a couple of years ago because there's now a 17-storey building built on that particular site. Much larger sort of catchments, of course. The Murray-Darling Basin is the largest one in Australia. It drains 1/7 of the Australian continent and starts up in Queensland, New South Wales, Victoria, flows down to South Australia, and also includes part of the Australian Capital Territory as well. Just in a slightly different thing for those people here, because we've got people from all around the world have joined us today, and I think that's great. In the Indian subcontinent, 3 very large catchment areas there. The Indus River, rising of course in the Himalayan mountains and flowing down towards the southwest there, circling around the western side of the Thar Desert. On the northern side of the Himalayan mountains we have the Brahmaputra River, flows parallel to the Himalaya ranges there for quite a while before it cuts through the ranges and makes its way down where it actually flows into the Ganges, which of course is the largest catchment that we've got in this particular area there. And you can see the rivers coming out of the Himalayan mountains there, some of them running off the Deccan Plateau to the south and finding their way into the Bay of Bengal. Right, rivers play an important role in shaping the landscape around us. This particular picture here comes from South America. The mountains there are being pushed up by lots of action in terms of tectonic plates crashing into each other and grinding against each other, pushing these mountains up. And of course, once they're pushed up, of course, the rains start to pour down on them and start to erode away the particular land surface, and in this particular instance we've got these very steep V-shaped valleys in the headwaters of that particular catchment area. It's only very small headwaters because it's very soon that the actual Amazon River flows out into that large plain, which of course heads off to the Atlantic Ocean thousands of kilometres away. Topographic maps are useful in terms of identifying where catchments are. This particular one is an extract from the Brisbane River area, and you can see sometimes how difficult it is to interpret these maps. You can see in the northwestern part of this particular map there's quite some rugged terrain there, quite a lot of ridges, narrow valleys, and so it's quite interesting to try and actually work out where the catchment boundary is between sub-catchments of the main catchment of the Brisbane River in this area. Quite complicated on the northeastern side, not so difficult on the southeastern side. North Queensland, where we have the ranges come down quite close to the coast in this particular area. When the winds blow off the ocean, as they frequently do, they are pushed up against these mountains here, they rise against the mountains, and as they rise, of course, the air cools. Because the air cools, it can't hold so much moisture, and so the moisture condenses out to form clouds. Probably in many instances those clouds will evaporate later on in the day. Sometimes they'll build enough so that we get quite a significant amount of rainfall in that particular area. That happens in a number of parts of the world, which we'll see in a couple of seconds. Okay, there's the diagram to represent what we've just looked at. We've got the wind coming in off the ocean, being forced to rise by the mountains in this area, clouds forming, rain falls, but the interesting thing is that the rain falls on the ocean side of the mountain. Once the winds hit over the mountains, we tend to have very little moisture in them, and so we get what's known as a rain shadow in that particular area. That means we've got quite different hydrologic regimes in that area, quite different runoff and types of runoff in those sorts of areas. There's quite steep, fast-flowing rivers on the eastern side of that diagram, quite slow-flowing rivers on the western side. Thanks. Great Dividing Range comes down right down the east coast of Australia, and so we have that effect. And it's very, very pronounced in the northern part of Australia, not so much further down the coast here, but we do get a separation of the rainfall patterns with the rain on the eastern coast areas and the much drier inland areas. And the diagram we've got there in front of us, you can see some of those shorter rivers which flow out of the Dividing Range in this area, and then the much longer rivers which flow down to the South Australian area there. Of course, that's the Murray-Darling Basin system there. Thanks. Right, that's just a classic one here. I was on the Barrier Reef a couple of weeks ago, and this photograph just shows exactly what we've been looking at, how the mountains here have built the clouds have built up against the mountains, and when I left Port Douglas that particular day, it was quite cloudy and overcast. It had been raining earlier in the morning, but just a couple of minutes later we're out on the outer reef, and it's a totally different scene because we don't have the same sort of build-up of clouds in this area. It's just a pity I didn't go the other direction over the range instead of out of the reef, because over the range is a town called Mareeba, and it prides itself on having about 300 rain-free days a year. And it would have been interesting to compare Port Douglas and Mareeba, but unfortunately I was going to the reef that day. Right. Looking at other parts of the world where we have the same sort of thing happening, right? The monsoons in India are very important weather pattern in that particular part of the world. The wind blows in from the Indian Ocean, Arabian Sea in the southwestern there, and it sweeps across the Indian area. It's called the Western Ghats there on the western side of India, and the rain, you know, they do force they're only about 2,500 metres high, not very high really, but they're high enough to push those clouds up and get the rain falling in that particular part of the area, so you get a drier Deccan plateau. But then as the winds go out across the Bay of Bengal, they pick up more moisture, and of course they bump into that Himalayan range in the northern part of the area there, and that forces the rain-bearing winds off to the northwest there. Lots of the rain falls on the mountainous areas, and of course lots of the rain falls on that North Indian plain there too. Very important for that particular part of the world. Right, sorry, Northern Australia also has an interesting pattern in terms of monsoons, because we get virtually a 6-month dry period and a 6-month wet period. This particular time it's coming back from Kakadu. You can see it's coming up behind me quite quickly there, and there's quite heavy rain falling in that particular area at that time. Right, here we are again, looking very clearly at what's a catchment boundary in this particular instance. This is the Inderfluve here. Any rain which falls in this area in front of me here, or in front of the slide you're viewing there, will flow into the Brisbane River and be part of the Brisbane catchment. Right? If it flows, however, if the rain falls on the other side of the mountain, that's the Brisbane River there. It's not a very long river. You can see those mountains in the background there. And if the water falls on the other side of the Great Dividing Range, then it starts a very, very long, slow trip virtually right through the Australian continent, as we've seen in a couple of slides so far, and until it reaches the ocean. Of course, some of it never reaches the ocean because it's used for agriculture, urbanization purposes, urban purposes along the way. This was a result of a particular storm happened as I was going through this area. You can see the runoff here from quite a very flat area. It's sheet flow across the surface there. Sorry, until eventually it comes into the drainage channel in the foreground here. And as I said, that water will find its way eventually, some of it, to South Australia. Some places, on the other hand, can be dry for years and years and years at a time, and then all of a sudden we get a lot of rainfall in a very quick period, and you have quite quick flows through these particular environments. Right, now we've looked at the rainfall, precipitation, and that particular aspect of hydrology. What sort of things now interfere and impact on the amount of runoff which we get in a particular area? This slide we've got here shows quite distinctly the impact of the rainforest in North Queensland. This is the Daintree rainforest here. You can see that except for the road in this area, the actual vegetation cover is quite complete.
And just on that point, one of the key elements as an engineer that we see in this particular photo is a discrete variation between surface roughness, obviously in the form of Manning's End from an engineering perspective, and where we might expect on the gravel road in the foreground that Manning's value may be as low as 0.02, or reaching up to quite high values as we get up into the upper reaches of that slope, where the Manning's value may rise to 0.15 or greater.
Thanks, Gavin. And the interesting thing here, of course, is that it's such a closed canopy, it makes it very difficult for the rain, when it does fall, to actually get through to the lower layers. Now, the rainforest depends on this water getting through to the lower layers, and so they've adapted quite significantly in terms of, right, the whole canopy acts virtually as a sponge, collecting water, and some of that water will evaporate back into the atmosphere, but if the plants, and many of the plants in rainforest areas are specially adapted, and they have leaves like this particular macaranga plant which I have in front of us here, has a large leaf to catch a lot of water. Then it has a very sharp drip tip, what's known as a drip tip point on it, and that directs the water to the ground. But of course it takes a bit of time for the water to come out of the canopy and down onto the ground. If we have an impact, in some areas, of course, where fire occurs, then of course the whole system is changed, and so rain in this particular instance would get through to the ground level very quickly in part of this area, but in other parts of the area, of course, it will again be intercepted by the vegetation in that area. And of course, the Uluru Rock is quite an interesting catchment for water too, because the water just pours off that rock if you're lucky enough to see it. Right, in the Indian subcontinent again, we've got this very, very large alluvial plain. It's called the Indo-Gangetic Plain. It's made up of the plain of the Indus River and the Ganges River, and of course there's only a really small rise between those two catchments separating them, and of course the mountains of the Himalayas separate them to the north. But once the water flows out of those mountains, it runs into quite a variety of materials that have been deposited by the rivers over a particular time. So silt, clay, sand, gravels will all have an impact on how much water actually makes it through that particular catchment area. Right, desert areas, sand dunes like this one just near Uluru here. The runoff from that is going to be very small unless there's a very, very, very severe storm. In some areas the flow of the water is very, very rigidly controlled. This is of course Bali, the rice paddies there, and virtually they control the flow of the water down to the last teaspoonful.
And in this particular situation, again from an engineering perspective, these are relatively complicated systems to model, and at times that an engineer will need to make decisions to simplify how this system could be modelled, because again we have these steep contrasts between some of the core parameters such as catchment slope as we see, but also depression storage, and again that management of the water in this particular location.
And moving along, this interesting set here just shows how urbanisation affects infiltration rates. Both Gavin and I come from Redcliffe. Gavin's moved on, I've stayed there. But in 1957, on the left-hand side of the screen, you can see there was quite a lot of bush. You can see a couple of catchment areas down there on that particular photograph. 1987, we're starting to get development occurring through the peninsula. Quite a lot of vegetation is being replaced, of course, by roofs, car parks, streets. So there's lots of interception, lots of runoff. We get over to 2014 and virtually there's a nice little green square in the middle of your image there, which is the Redcliffe Botanic Gardens, and most of the rest of the area, unfortunately, has been cleared for urban and industrial development. Right. Types of floods that we get, many different types. The very quick one, right, is the flash flooding. It can be natural or human origin, often occurs with little warning. You often hear of campers being trapped and sometimes unfortunately swept away when we have heavy rainfall in a catchment with very narrow valleys, or we have the failure of a dam or levee in a particular area. Then we've got the other two sorts of floods, the rapid onset flood. It'll rise quickly over a couple of days and fall away just as quickly. Right? Many areas experience this type of flooding. Where we've got low, flat areas, like we've got in the western side of the Great Dividing Range in Australia, we get what are known as slow onset floods. We also get them in the Indus River too. We saw them a couple couple of years ago, and these rise over a period of days and can take weeks or months for the flood level to fall. Many factors affect the type of runoff and flooding which can occur in these areas. And just to show it in a graphical form, we get the rainfall, but as you can see in the diagram here, there's some time, a lag, between when the peak of the rainfall occurs and when the actual main runoff occurs. And there are lots of reasons for this, some of which we've just looked at: the sort of vegetation cover you've got, the soil and rock type you've got, and what sort of agricultural use you've got of the area. And just quickly looking at an example of this, this is one of our rapid onset floods here. Barron River, made famous for the Barron Falls in North Queensland. Unfortunately, many people will go there and see them looking something like this. But if you're lucky and there's been a bit of rain around, you'll get something where the falls actually become quite major and significant and quite spectacular falls, usually within much quicker than 24 hours of rain falling in the catchment of that area.
And thanks, Dave. That's a great overview of the physical characteristics of the hydrology process that practicing engineers have to deal with. And we felt it was a very good overview to see it in that sort of format, to take some of the numbers away from general hydrology. Unfortunately, me being the engineer, I might bring some of the technical elements back onto the table. And so just as a quick overview of what David's just described, we have these functional components. We've had precipitation, that variation between those flash flooding type characteristics, monsoonal rain patterns, broad area flooding. We have the losses, the evapotranspiration, storage, infiltration, and then of course you take those away from each other and we can derive our runoff. From a software perspective, the graph in the middle there highlights the variation that you get between hydrograph is functionally the storm itself multiplied by rainfall intensity. The magenta line, the infiltration, is lost, so we don't have any runoff. We can see quite clearly we've lost surface runoff from that component, and as the storm continues to build, we get to see the peak that is actually quite delayed relative to this. Well, it is actually a small catchment, but we've got about a 15 or 20 minute delay relative to the point at which the peak rainfall itself occurred on that hydrograph. From an engineer's perspective, we typically look at two types of storm analysis. We have design storms and historic storms. And that's often a difficult question to try and deal with as to what should a user potentially model. Historic storm data is generally easy to obtain from the Bureau of Meteorology or your local state agencies and authorities who may hold those records, but that's typically only in the form of rainfall data. Getting information to apply to modelling, to calibrate, can become a lot more difficult when you're trying to get into the analysis of any given catchment. Design storms, however, around the world are widely utilised by engineers, where simplified information can be provided by, again, the authorities in your particular region in the form of temporal patterns, with intensity information in the form of either intensity, frequency, duration data, or again, historic rainfall if you're looking at a particular event itself. Historic storms are typically obviously that function of observed rainfall, but are used to identify how major catchments in particular perform, and particularly important if you're looking at trying to calibrate a numerical model against a real-world situation. For example, the Brisbane River catchment at the moment is going through a big update to its analysis pursuant to the major flooding that was in this particular part of southeast Queensland and the broader Queensland area in 2011. And of course the key part of that is to try and validate that information and also provide our Bureau of Meteorology with improved data to forecast the impacts of flooding in terms of providing flood risk warnings to the community. This is just a simple graph which sort of showed how over a course of a rainfall event that infiltration can actually be quite a dominant parameter versus rainfall. So we've got flow as the blue line at the base, and you can quite easily see that we've actually lost these components of this particular catchment, which is a rural catchment, and we only have these tiny blips in rainfall, in runoff, I beg your pardon. But models can quite easily assess this. Again, it's getting the information to compare it against that makes this type of analysis difficult. From an engineer's perspective, again, we need to understand some of the statistics behind what we're trying to analyse. And that makes us look at event frequency, the probability of said events, and trying to get a generalised relationship between the two. A standard example is what the newspapers like latching onto will be a statement that any particular storm may be a 1 in 10 year event or a 1 in 100 year event. But what does that really mean? And so functionally, if we look back at our historic records, if a given rainfall occurs 10 times over the previous 100 years, if you have 100 years of record, well then we might generalise that statement to say that, well, it's a 0.1 storm or a 10% storm or that 1 in 10 year storm. Functionally, those statements all hold true, but again, it does lead to the potential for misrepresentation, particularly in the media. Some areas are moving away from talking about the 1 in so many years relationship, annual exceedance probability option, but again, that's that's not widespread, although it's certainly happening in Australia. Because the big thing is, if people say I've had this so-called 1 in 100 year storm, there's clearly a risk that is implied against that particular rainfall event. And as engineers, we're typically risk-averse professionals, and of course we need to ensure that we're providing the community with the best potential engineered solutions from planning perspectives, and look at being able to provide mitigation options in response to these sort of storms. Just a quick summary. I won't go through this one in a lot of detail. David's done a great job talking about this generally, but these are the core parameters from storage and loss perspectives, where again, relative to our inflows and pursuant to our inflows, losses do occur. And losses are not in that way subject directly to the storm itself. Again, we have these long duration runoff events that exist beyond the Great Dividing Range here in Australia, where a lot of places and towns along the way, along the Murray-Darling system, they'll typically have what's called as sunny day floods. The rainfall may have occurred 2 weeks prior to the event, and they can be having a great day when the flood turns up. So these losses are definitely a continuing element relative to our rainfall. From a modelling perspective, in a lot of software packages we have these typically standard loss methods that are available to us. I won't go into these in a lot of detail today. Is definitely a 101 type discussion. Didn't want to sort of bore people with the calculations on this particular front. But the core ones being Horton, which is a initial and asymptotic decline method. Don't stress too much about those lovely terms. But where we start with a high initial infiltration, and that then weans its way down to that ongoing infiltration rate, which, depending on the catchment characteristics, may be as low as 1 or 2 millimetres per hour ongoing. And that's the kind of information that's definitely important in those long duration sunny day type flooding situations. So Horton's method is definitely a loss method that can be used as a continuing loss method. The common one in Australia, I'll sort of skip over GreenAMP. GreenAMP is used definitely in the United States and other key parts of the world, but the main one that design engineers that use design storms apply will be the uniform loss methods, whether they be in proportional losses, where a proportion of the storm itself at any given time frame is lost, or initial and continuing losses, where you can have a burst component and then an ongoing hourly rate loss, or again an initial and proportional loss. The SCS model is the Soil Conservation Service model, where again it's similar to an initial loss, but a fraction of the initial loss abstraction pursuant to that point. Again, this is sort of a modeller's overview, where we need to apply our rainfall, subtract our loss model, identify the excess hydrograph, which we sort of showed on a slide previously, multiply that by the catchment area, and from that we'll be able to derive an instantaneous runoff rate. When we calculate that out over a long storm event or a design storm event, we'll get a dynamic hydrograph. We can route that calculation through a storage model, and then we'll determine our final runoff hydrograph. Some of the key parameters that a modeller needs to take into account, of course, are dominated by the catchment area itself. Rainfall is important, whether that be in intensities or rainfall depths, depending on how you apply it to the software. Catchment slope does change the performance of response times. Catchment roughness, where David showed that great shot up north with the variance with the forest and the road environment. And some particular methods do apply catchment width and length to their calculation sets. And finally, the land use characteristics may also affect the loss. For example, a car park would have obviously a very low initial loss or continuing loss, again versus that forested or undeveloped environment. And so what do we want to produce when we undertake a hydrology study? And obviously hydrographs are the key output, where we're trying to derive peak flows and volumes. These results are functionally related to that rainfall frequency, and in this few slides I've shown the sort of variation between a continuous simulation shot, we saw that a couple of slides ago, it's the same shot, to a very intense soil conservation service hydrograph, which is a centrally weighted 24-hour storm. And that particular storm is actually used in New Zealand, Korea, parts of Japan and Canada, as well as widely across the US. So it's not commonly used in Australia, but can be at times. And on the right-hand side we have an Australian temporal pattern 60-minute 100-year storm. And essentially the analysis of this information is really the hard part. From a routing perspective, we have a number of hydrology methods available to ourselves within the engineering fraternity. The most basic of these, or the simplified method, is definitely the rational method. And then we have some more dynamic hydrology methods in the form of Lawrence's method that may also be referred to as the rafts method. One thing I do note that rafts, which you can utilise in XP rafts, actually stands for the runoff and flow training simulation. So in and itself is not actually a model. The SCS methods, those soil conservation service methods, and unit hydrograph methods such as the time area method are available. Unfortunately, this is not shown quite well on my PowerPoint, but we get to see the variation. We have the overall view that you would get in your results set to the left, showing the full storm. We've got the runoff at the lower component of this graph versus the total rainfall, which is the blue dashed line. It's a sort of mimicked, actually, I beg your pardon. You can see the rainfall excess relative to the infiltration. Evaporation is right at the top. It's quite low in this particular model. For this particular graph, it's only showing about an hour and a half of time, and you might expect on any given day, even in a relatively arid area, evaporation rates in the order of 5 to 10 millimetres per day on a particularly dry day. And of course, you don't necessarily expect particularly dry days prior to or after a rainfall event. From our software in XP Swim, there are a number of hydrology methods that are available to engineers for application. The rational method, again, is the simplest of these, which is derived from this term of identifying the time of concentration. And from that you're deriving the critical storm. It's very much a simplified method. We have simplified coefficients to basically incorporate your losses relative to the total catchment area. The intensities are derived based on this time of concentration. You'll look at an intensity frequency duration table. If, for example, you had a 15 or a 25 minute time of concentration storm, you would expect a relatively high intensity compared to a long duration storm that may cover in excess of 24 or even as high as 72 hours from a design perspective. Lawrenson's method, or the rafts hydrology, is definitely widely used in Australia, but it is also used in parts of the Asian areas, China, etc. And what this particular method does, it takes your total area, undertakes an additional calculation to subdivide any given sub-catchment into 10 equal areas, routes those through each other using a storage equation, and the result of that is a dynamic hydrograph. And it's a well-known and well-reported method, and if people are interested in more information, they can obviously contact us to find out more about this method, but it is also detailed in the Australian Rainfall and Runoff documentation as well. That's just a quick summary. Again, I didn't want to go into too much maths in this presentation, sorry, and but that is the core equation and the parameters there, and by all means come back to the slides, which will be available for download after this webinar. The time area method is derived in England, and it is functionally a modified rational method. That's probably the simplest way to describe it for those who may or may not have struck this particular method. But we do get to utilise variable rainfall components instead of having a static storm. And again, that's the kind of output we see on the bottom right hand corner relative to the catchment area top left. Now, the development is one of the key things that engineers do want to assess, which is that change between the impervious characteristics mainly, and when we change the impervious characteristics, we inherently change the roughness values. These two screenshots here, these two graphs, show on the left an undeveloped catchment with a 0% impervious rate, and on the right hand side going to an urban residential scale level of impervious coverage at 60%, and we get to see quite quickly that we're going from 335 litres per second as discharge up to 565 litres per second. Now, whilst they don't sound like large numbers, if you were to extrapolate this catchment out, which is only covering, I think, a single hectare, as all this particular model was, a simple model we set up, extrapolate that out to regional catchment wide changes, and urbanisation has significant impacts on our natural systems. And of course, you may wish to, from a hydraulic perspective, look to resolve that with engineered solutions. And just before we wrap up, the latest, I suppose, advancement to hydrology that is now available to the engineering fraternity is direct rainfall or 2D rainfall. And it is being seen as a simplified method. In part, I will say that it is taking the engineer away from hydrology at times, where the most difficult thing to define is the first point that David discussed earlier, which is the identification of those major interfluves, those major catchment boundaries. Once you've defined your major catchment boundary, you can apply a polygon using a GIS method and apply rainfall directly over your catchment to a digital terrain model, and apply losses based on land use on pure areas, instead of collating those into simple tables of data that you would do in a more traditional sense. And surface roughness also needs to be defined based on a GIS environment. The outcome of that is that you are able to produce or assess the impacts of localised obstructions that may be difficult to assess, like we've seen in the barley example, where we have those rapid changes of storage in the rice paddy situation. That's not saying that 2D models particularly love doing those kind of steep slopes, but it could be done. From inside the model, from a modelling perspective, you do need to have good data. And the most difficult data to come by is typically the terrain itself, and thankfully with advances in aerial data capture, in aerial photography and LiDAR techniques, we can quickly apply that information if it is a variable in your area. And we can see here I've just drawn a simple polygon over an area, and where this orange shaded polygon sits is the area that I'm going to say rainfall will occur to assess the performance of what in this particular example is actually a minor drainage or pipe network system. From a dialog box we just simply need to say this is the rainfall I wish to occur in this zone, and I would also define other elements such as buildings, road land use characteristics, and then analyse the performance at the creek at the northern end of this site. So that's sort of the more recent change to hydrology. That's the end of our session today. Hopefully that wasn't too stressful a session. We wanted to keep this nice and simple to talk about those physical characteristics and also some of the methods that are available to engineers and designers, and we really do welcome any questions. If you haven't been asking them in the background, I've certainly heard my colleagues typing away busily in the background. If there's anything in particular you think of pursuant to this session, by all means contact us on the details at the bottom there. Obviously we are the Asia Pacific zone, or via our email address, which is ausales@xpsolutions.com. Thank you very much for your time today.
Thank you.
And thank you, David.
Thank you.